it's just x inside. It's just, you know, the derivative of 3 to the something is what? What's that rule?
3 to that.
3 to that thing.
Times 2.
No.
3 ln 3x.
3 to the thing,
Yeah.
ln base. Yeah, so a to the x, its derivative is a to the x, ln a. So 3 to the something, its derivative is 3 to the something, ln 3. Now you bring in
chain rule, which is 2x.
yeah, derivative of x squared. The chain rule comes in. I'm going to let you absorb that. It's one of those rules that really quickly gets forgotten because e to the x is so nice, it's its own derivative, and then suddenly we throw 7 to the x at you in Math 280, and people are like, oh, I don't know this. Oh, that's too bad for you. So a to the x in general, you got to tack on that ln a. E is the one, ln e is 1. So it's not going to show up. But it follows the same rule. And then like somebody over here said, derivative of x squared is
2x.
yes, you can say 2x ln 3, gather all that mess, times 3 to the x squared. Cool, I like it. What I don't like is when somebody gets a 6 out of here somewhere. Where would somebody get a 6 from? They're multiplying the 2 and the 3, and they're like, Jeff, it wants to multiply. No, it can't. Right, this is just 1, 2, and this is x squared number of 3s. Holy shit, so you can't multiply that base by something. Yes. Alright. What is it for? Alright. So, this guy, how am I going to rewrite it? First off.
Tangent 3x minus 1 raised to 1.
Good. So, rewrite any root as a power. Cool, I like it. What's the outside function here? Tangent. So the very first step is forget that the inside is something weird. You don't have to think about anything about the inside. You just go, what's the derivative of tangent? Secant squared, kick ass. Times mess. Not times, but of mess. Thank you. And man, when I say mess, I don't mess around. That is really a mess. And then, of course, what am I not done yet?
Chain.
Yeah, the chain rule. So now I've got to do the times the derivative of the inside.
There's also the 1/2.
Wow. There we go. So again, I'm just going to write the rule down. Because when you start getting multiple chains, you get really lost if you're trying to do it all at once. It's a little crazy. And that's when people start to think, I'm supposed to know how many I'm supposed to do. No, you don't have a clue. Now my whole world is that. This thing at the end, the beginning part's done. So the beginning part is just going to sit here and wait. Secant squared of this. And then how do I take this guy's derivative here?
1/2 3x minus 1 raised to the negative 1.
Yeah, the 1/2 comes down. 3x minus 1 to the negative 1/2.
Times 3.
Times 3, cool. So that was the last little Russian doll that comes popping out. And you're like, holy crap, that was smaller than I thought. So that inside of 3x minus 1, you got to take its derivative. Cool. I like it. So I don't know, I really want you guys to click on to this. And sometimes people aren't looking at it correctly. What's making me do what I do? Tangent made me put secant squared of the stuff. And because the stuff on the inside was not just x, I got to take its derivative too. Something to the 1/2 power, 1/2 of that thing to the negative 1/2. But then again, the inside thing again is not just x. I got to take its derivative too and link it on. That's why the name chain rule is kind of nice. You just keep linking new things on as long as the inside function is something. I've never had somebody do like times 0 because the derivative of 3 is 0. But I don't need. There's no more derivatives to do. The 3 is an answer to a derivative. It's not an inside of something. All right, maybe. And then you can clean this up a little bit. So you can square. Let's bring the root back in so it looks a little cleaner. That's on the top. And on the bottom, let's see, there's a 3 on top too. And the bottom is going to be, what's going to be on the bottom? 2. Square root 3x minus 1. Kick ass. Yummy, yummy. I don't know. If you just left this, I'd put a note at least. You got to at least take the 3/2 out in front as a coefficient, right? All right. So what about, let's see, let me go to another nice clean sheet. The next one out. This one sounds familiar, but I don't know. Maybe just help people out. This is kind of related to the ones in the book where they'll say find f, the nth derivative of f. People kind of freak out a little bit. Like, how the hell? I didn't ask for the nth derivative, thank God. Just the second. So what do I have to use to get the first derivative? Product. Yeah, so that's my whole world at first. It's a product of functions. Right? Chain rule is normally not, well, let's see, I don't know how to say it. Chain rule, is, in this case at least, is not the primary thing. It's just product. So the derivative of x1 times e to the 2x plus x times the derivative of e to the 2x. We put a 1 there. Okay, I like it. And then what does this involve here? Chain rule, okay, yes. So then you get e to the 2x plus
2x squared e to the 2x.
We get a lot of different answers. So let's see. Here's x. The derivative of e to the anything is itself times the derivative of the inside. What's the derivative of 2x? 2. That's better. Gather x. So then we get e to the 2x plus 2x e to the 2x. That's f prime. And then to get f double prime, I just attack this thing again. Yeah. So then f double prime, how do we get that? Yeah, so here's the interesting thing, and here's where we got to be really careful. Let me do a little side note. You do whatever you want to do. E to the ax, its derivative will be what?
E to the ax times a.
So a e to the ax, and then people go, oh, so the stuff on the top comes down. Well, right off the bat you can see that that's wrong. Ax didn't come down. Why is there an a in front? Because it is the derivative of ax. So if I see e to the ax squared, how do I take its derivative?
2x.
Let's see, it'll be e itself. Yeah, I just said e itself. Times the derivative of the inside. This is what you guys are saying?
It's 2a.
2ax. Kick ass. So 2ax e to the ax squared. I like it. Whoa. So very often what we do is we can generalize this. The derivative of e to the u. If you ever see u in a rule, it's understood to be a function of x. So u could be ax squared, you can be whatever. E to the u's derivative is going to be e to the u times u prime. And that's really just the definition of chain rule. I like it. But if it's linear, it kind of kicks ass. If it's linear, the coefficient just comes out. It sort of looks like the power rule, but it's not. You got to be careful. Don't overgeneralize that. So the derivative of e to the 2x is just 2e to the 2x. And what has to happen here? Kick ass, prodigal. So the derivative of 2x, 2, plus 2x times the derivative of e to 2x. 2e to the 2x. So I get 4e to the 2x plus 4x e to the 2x. It's f double prime. Become a double. Kick ass. And then you could take even more derivatives after that. Alright. So really the only kind of function we've seen so far that'll disappear after a certain number of derivatives is what kind of function? What kind of function will disappear if you take enough derivatives? Will become 0. That's what I mean by disappear. What kind of function will disappear? Will e to the something disappear ever?
No.
No, it won't ever disappear. What will eventually? Constant, yeah, cool. Constant's a nice one. One derivative, it's gone. You've killed it. Right? How about x plus 1? How many derivatives will collect? 2. One derivative makes it 1, and then another derivative makes it 0. So polynomials. Every polynomial, there's going to be a certain number of derivatives that will kill it, that will make it 0. Some of you guys I talked to sometime, I can't remember if I said this in class, but we call it an annihilation operator in differential equations. It's the operator that will kill it. Right?
What about like when it's to like a radical? So it's like 1/2. So that will never die off.
Yeah, radicals won't die off, will they? Because you can never get to the 0th power with fractional exponents. Does that make sense? So it's got to be polynomial. So far, that's what we know. All right, I like it. All right. Did we go over these here? This sounds familiar, maybe. Did we do this one yet?
Yeah.
Yeah, I thought we did. So let's see. Let's do it again real quick. So if I want to take this guy's derivative, I've got to use product rule here. Right? Does this sound familiar? This does sound familiar to me. So how do I use product rule here? Yeah, 2xy plus, so derivative of x squared times y plus x squared times the derivative of y, which is dy dx. And then what's the derivative of cosine? Negative sign. So minus cosine becomes positive sign. Sine y, and the inside is y, so I have to dy dx. Yeah. There we go. Equals derivative of 3x. Awesome. Derivative of 2y squared.
4y dy dx.
Some of you guys are realizing anytime you take the derivative of a piece that actually has a y in it, there's going to be a dy dx attached to it. Just chain rule. And now it's algebra. I would not give this to my algebra students to do, but I could give one that's almost like this if I replace sine with m and dy dx with b, and I say solve for b. It's the same damn thing. So the level of work required here is mathematic. How do I do this? Yeah, get all my dy dx stuff together. Right? When I have more than one variable, it's funny how quickly people forget how to solve something like P plus PRT equals A. Right? That's the principal rate time, the interest formula. Say solve for P and people freak the hell out. Right? But when there's more than one variable that you need, you get them all on one side and you can factor the damn thing out. No big deal. So here, I want to move, let's move this guy this way, and this guy will move that way. Swap. So let's see what we get. X squared dy dx plus sine y dy dx minus 4y dy dx equals 3 minus 2xy.
Factor and divide.
Yeah, exactly. Right. So now you just take the deal with the reason you got them all together was so you can pull the one out. Right. There's not really 3 of them. There's just one of them. Let me see if I can jump to this next step. Divided by all the coefficients here, right? Of my dy dx. Divided by x squared plus sine y minus 4y. I gotta write a little worse. You can almost see what it says. Just a little worse. There you go. That's worse. It should be the letter Y. Yes, ma'am.
Do you only assign the dy dx to the derivative? Like, because x squared dy dx is that, or where, like, how do you know where to put dy dx?
Oh, okay. All right. So, as you're working the problem out, so let's kind of do the first step again on this problem. All right. So, when I'm taking the derivative of x squared y, you can still see it. not even, you don't have to know implicit, you have to know shit. You just have x squared, which is a function of x, times y, which is a function of x. So you have to use the appropriately named product rule, because we have a product of two functions, right? So that's, that's all you got to do is say, what's the main thing going on here? Product of two functions, product rule. So that's the first thing I do. So then if I write the rule down, it's x squared derivative times y plus x squared times y derivative, right? I'm being a little less good with my notation, but oh well. And then it's the rest of the shit, blah, blah. But just to finish this piece out, what's the derivative of x squared?
2x.
2x. So it's 2xy. And what's the derivative of y? dy dx. So it's not, you don't have to know, when do I put it? No, it's going to come out naturally. Of course it's going to come out. It's either going to be, I'm taking the derivative of y, which is dy dx. That was like in your face. Or on the cosine, why would it show up?
It's cosine 1.
Derivative of cosine is negative sine, so it makes it a plus. Chain rule says inside's a funky function, right? I don't know what the hell y is. So then I have to times by the derivative of the inside. Yeah. So I don't want you to feel like, how does he know when to put that on there? No, it's just the rule. I'm following the rules. That's all I'm doing. Right? Okay, I like it. Just because they didn't tell us what y was. If they told me that y was the square root of 3x minus 1, then it would be a lot like this one. Right? So if I did this one, like if this was tangent u, what's its derivative?
Secant squared. Would u be the y?
Yeah, u is some function of x.
So du dx?
Du dx, kickass. Right? I like it. And then, so if, let me see, where's the answer? Blah, there it was. Blah, 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 that mess. So watch. What is, if u is square root of 3x minus 1, which is 3x minus 1 to the 1/2. Stay with me. If that's what u is, and that is what u is, right? I just put u in there so I didn't have to look at the ugly radical, right? Now watch, and then this is just the rule. So if u is this, what's du dx? Good. So all this stuff would have to go here in place of that. And that's exactly what we got. That's where that came from, is from the derivative of u, the derivative of the inside. I'm having trouble saying derivative. Does that make sense? I mean, so it's not something like, how does he know? Or when do you put that thing on there? It's the rule tells you that's what you freaking got to do. Realize that's all it is. It's just the rule. I'm following the rule. So when the rule says the derivative inside is a y, I got to multiply by dy dx. It's got to get its turn. The same reason we multiplied by this mess. Same exact reason. It's just not as messy. They just say, let's just call it y because it's disgusting. All right, we'll just call it y. It's cool with me. Maybe. All right. Where was I? Here it is. All right, so that was that guy. So if I want to know the derivative somewhere, somebody would have to tell me, what would I eventually have to know? I have to know both parts of the point, right? Obviously. This is not, can you guys realize this is not a function of x. This is now a function, the slope is a function of x and y. All right, not a big deal. I don't think you guys have seen the notation for that before, though. Remarkably enough, the notation is f of x, comma, y. Yay. So the derivative we found is a function of two variables. This is the closest we get in this class to functions of more than one variable. A lot more to it than that. So let's do b here, and then we can do c down here, because it's all about that. So how do I do part b? What's the main thing on the first part of part b?
It's a function of...
We can rewrite it here so we see what the hell we're talking about. Is it who what?
Disgusting.
Aw. Dude, if you think that's disgusting, just wait. Wait. I can make
cosine times the derivative.
Yeah, good. So it's the derivative sine is cosine, no big deal, but the inside is going to require its own derivative to be done. So I just put it there so I can look at it in a minute. How we doing? You alright? What's going on?
I hate that next part, the product part.
Oh. Alright. And then this I can write as y to the negative 1, right? So what's this got? This derivative? What happens? So much.
1 plus
Yeah, good. The negative comes out.
1 over y squared dy dx.
I like it. So it becomes plus y negative 2. Holy crap, I'm running out of room. dy dx.
Equals e to the x.
I like it because it's its own derivative. Alright, cool. I like it. I like it. I like it. I don't know if you realize, you probably do, you at least feel this. We've actually gone like light speed ever since we did 2.8. The rules have just come fast and furious. And again, every single thing we've done so far, you could set up the limit definition and somehow prove, but it's so much better to go, well, this always happens. X squared always becomes 2x. And then we kind of built on that. We built the product rule. We built the quotient rule. We built them so we don't have to do the limit definition every damn time, which that part you guys appreciate. But now we're able to do so freaking much. Holy shit. We went from being able to do nothing to every damn thing almost. Alright? So how do I... I'm sorry. But that... You don't like that, but... This is not that bad, right? I mean, the product rule is nice. What's the derivative of x? That's funny. Times y plus x times the derivative of y, which is dy dx. That's all. So anytime you have x, y, you just know it's going to be that.
I hate what it does for the problem. It gets out of hand.
Poor little thing. It's not its fault that it exists. It just happened. It just came out of there. Plus, you're like, we should fix math. We should let it not make any more things. Aw. That's horrible. It took such a weird turn. Alright, so now I just have to... What's the best thing I can do here to help me on the next step?
Distribute and then...
That's right. And my God. Alright. I'm going to continue on your homework to be very emphatic when you make very basic mistakes. All right, so I don't mean to make you feel bad. I mean to say this should not be happening. This should hurt. So I still have people that divide by x, y or something so they get cosine by itself. That is just not acceptable, right? It's unacceptable. So now to distribute this, what happens? Do I get cosine xy squared?
No.
Hell no, right? I don't have that magic. So y times cosine xy plus
x cosine x dy dx.
I like it.
Plus y to the negative 2 dy dx equals...
Alright, kick ass. Whew. Whoa. Yeah, I ran out of Rubo's music. Sorry. Stay. Alright. So.
Subtract dy cosine.
Yeah, this is awesome. All my dy dx stuff is already together. Just got to get this dude out of the way. So let's see. I'll have dy dx that comes out of x cosine xy plus y negative 2. And I have e to the x minus this stuff. All right, let me stop there for a second. I'm sure you guys are with me. Make sure I'm with myself. Yes, so sorry. I took the dy dx out, and of course now I can just divide by that stuff. So I get e to the x minus y cosine xy over x cosine xy plus y negative 2. And if you wanted to multiply top and bottom by y squared, get a little tear out of me. That would be awesome. Why would I do that? So I don't have this negative, but it's not a huge deal. You could. And now we can use it to do what actually number 4 says. Let's see, did it capture everything? No, of course not. You rewrite that.
Or with C. Yeah, no.
Skip one.
Which I kind of prefer.
Oh, yeah, okay, gotcha. That was part B. I forgot. Alright, that's good. I don't need it then. You guys got that?
Yeah.
Hopefully, because now it's something else. Alright. Look at number 4. Now, of course, I kind of built you up to it, because on this part I asked you to do the implicit differentiation, and then I asked you to find the equation of the change line. You know this problem is going to come up at least twice or something, right? I mean, the process is very basic, but now we can use calculus to fill in the unknowns, whereas before we couldn't. So what's the first step to finding the equation of the tangent line? Good. So I can find the slope. It's like, I don't know you. So there is x cubed.
3x squared minus 3y squared divided x.
Beautiful. Kick ass. And just so you guys realize, again, I know I've said this kind of thing before, but when you take the derivative of x cubed, it really is 3x squared dx dx. It totally is. Of course it is. But what's dx dx? 1. Sweet. So we're always chain rule gets done. It's just that if you take the derivative of x, it's going to cancel. But dy dx doesn't cancel. Let's see, where am I? You went too far. Okay. Equals, and we got this xy business here, right? So I get 7 times y plus x dy dx. We already did the product rule for xy. Is that cool? No? Product rule for xy. So it's x prime y plus xy prime, 1y plus x dy dx.
Yeah.
You see that enough that it just should become a thing. And then you're like, Aaron's like, oh, again, good.
This one's not so bad, it doesn't have cosine.
Oh, okay, it was the cosine. All right. So there you go. So bring that through. Blah, blah, blah. Let's see, dy dx equals 7y plus 7x dy dx. All right, cool. And now you know the whole thing. I want to add those 3y squared blah, blah over there. Subtract this 7y. Is that cool?
Yeah.
I mean, this is algebra level now. Maybe. So I'll have 3x squared minus 7y over, let's see if you guys can handle this. It would be 7x plus 3y squared, right?
Yep.
Now this one's a nice example of, let me make sure you guys are with me. What? It's not what I was expecting. Is that a rooster? What was that? Yes? All right. Was somebody napping? I'm sorry.
I'm sorry.
It sounded like lemonade.
Oh, was somebody doing lemonades?
There was someone go.
Lemon grab, whatever you use. Sorry. All right. Half the class, what the hell are you doing? So what's the, alright, so is everybody with me on this? And I love, look at the symmetry, 3x squared on top, 3y squared on the bottom, 7y on top, 7x on the bottom. I love it. So that doesn't happen every time, but almost always when you do implicit, there's some kind of symmetry, and sometimes it's really, really in your face. So what is the slope at our point? How do I figure that out? Alright, I think you guys said to plug in the point. So 3 times
12. I mean 16.
4. 7 over 2, 7 times 4 plus 3 times 2 squared. We continue this over here. So the slope I get would be 48 minus 14. So 34 over 40. Right? 20 plus, yeah. So 17 over 20. And then how do I get the equation?
Just
However you want to.
5
Yeah.
11 plus 8. Or 0.2.
Right, just plug in the point, plug in the slope. There should be plenty of these in the homework to remind you how to do it. Oh, let me wake this guy up. Because this is kind of cool to see it actually in action. So what I was not able to see when I first learned this because we didn't have. Alright, I won't take you down that route. Back in my day, we didn't have all this newfangled serious shit. Alright, and so if we simplify this a little bit, what do we get? 17 over 20x minus
27 over 5.
7 over 5, yeah. Because you're adding the 2.
Oh,
Not the same thing.
yeah, okay.
I like it. Alright, so let me show you. This is kind of cool when you see it in Wolfram Alpha. While this thing is warming up, are there any... I think last time you guys got to do this yourself. I remember, and then I said, we'll do this, we'll go over this together next time, and then we did a little bit of new stuff. So, I like that. Anybody get something radically different, you're not sure why, or... Because now would be a really good time to bring that up. Alright, so let me show you what this thing is able to do. It's kind of nice. Let's see which one is it. Cool. See, I don't think I need to sign in for this. So if I plot x cubed minus y cubed equals 7xy. And then what did we just get? 17 over 20x minus 7/5, right?
Yeah.
Put y equals. Let's go from x equal to negative 1 to x equals 7. Alright, let's see what happens. It should be interesting. Because it's the point 4,2, so it's trying to like center it. I want to show enough of it so we see that loop. I think I graphed this one last time. I can't remember if I showed you. Did I show you that? The loop? Oh, it's off the screen a little bit. Oh, well. I want to get the full script. Yeah, let me go out a little bit further. Let's see. Negative 3.
That's so cool.
The magic is happening. Alright, this is kind of nifty. I like this. So, it's weird. It shouldn't have a point there. No. Alright, I'll be alright. Let me zoom in. Bring it back on the screen. Get out of here! What the hell? What's happening? Alright, so that point is nothing. What is that point? Yeah, good. Alright. And there really should be an intersection here too, but it just, I don't know what the problem is. It should intersect at 4,2 still also, but 4,2 is right here. So this is the tangent line. It hits at 4,2 and then it keeps going. So again, it's all about locally. So it doesn't matter that it actually hits the curve again anywhere else. It can hit the curve an infinite number of times. But locally it only hits it once.
Well, I mean, but so locally could be infinitely small.
Second.
Locally can be infinitely small.
Yeah, locally. What do you think? What do you think governs local? Delta. Yeah. I say x naught plus delta, x naught minus delta, and delta could be arbitrarily small. So you can redefine your definition of local could be, and again, it's just like the. You can think local is in this room, or you think local is our college, or you think local is San Diego, or you think local is California, you can think local is the United States. Holy shit! All right, so there's a comparison between the real world and math. Very often when I say local, or even when we say this, get ready, we say this in a neighborhood of. So in a neighborhood of 4, the outputs are going to be looking like a straight line. There's a problem in the homework that tells you to zoom in on something, and of course anything that has a tangent line, if you zoom in close enough, it's going to look like a straight line. We live on a sphere. When I look, it looks flat, and that's why, believe it or not, I don't know if you realize this, flat earthers still exist. Search it. They have a whole YouTube channel about why the earth is flat and why it doesn't look that way. And we've been to freaking space. What the hell else do we have to do? Holy shit. Right? And they're like, maybe we haven't been to space. Oh, God, don't tell me that too. Shit. So many weirdness concentrated in one thing. Alright, anyway. So Wolfram Alpha, I didn't have to sign in to do that. That's kind of nice. So it's really nice for plotting these functions that you couldn't possibly plot any other way. I can't solve that for y. I can't put it in my TI. Wolfram Alpha kicks ass. Okay. So there's no questions over that. We're going to get into some semi-new stuff here. So you guys are cool with that? Yes?
So one of the circle cases can you solve problem, solve the problems where you have x and y with only 1 point, or 1 part of the point. So
if they give you one part of the point, you might be able to plug that value in and solve for the other variable, right?
Yeah.
You might be able to.
Okay.
Sometimes it's impossible
Okay.
by hand. But the minute if I got an equation with 2 variables in it, I plug a value in for one of them, that's going to reduce my problem down to something that I should probably be able to manage, but not always. Yeah. Okay. Can somebody flip the light back on for me? Thank you. I'll do that there. Just want to come back. I think last time we talked about natural log. Did we? Started to? Okay. Whoa. Oh yeah, it's the person that has a really nice write. No, it's not me. Or no, this is my morning class. This is what happens to my writing as the day goes on. If only. It's never good. I don't care what time it is. So if I wanted to figure out, so here's the power of implicit differentiation. If I don't know what this function's derivative is, but I know what its inverse's derivative is, I just have to rewrite it in terms of the inverse and then attack it implicitly. What the hell do I mean? How do I rewrite this so it's x equals a function of y?
X equals e to the y?
Beautiful. E to the y. Kick ass. Let me stop there for a second. Come on. And now that's an easy ass derivative, right? What's the derivative of x with respect to x?
Well, 1.
Derivative of x?
Okay.
1. Derivative of e to the y with respect to x?
E to the y.
E to the y. dy dx. Why is the dy dx there? Because the chain rule is there always. It exists. And now how do I solve for dy dx?
So it's divided through e to the y.
Yeah. So it'll be 1 over e to the y. But what was e to the y? No, come on.
It's equal to x.
What's e to the y?
1 over x.
X. So it's 1 over x. So what did we just figure out? We figured out that the ln of x, if I take its derivative, I get 1 over x. It's crazy. And if you think about it, look at here's ln of x. And here is 1 over x. Now if I just try to draw this guy's slope. Now here's the other thing, before I get too far, I gotta remember this. 1 over x, what is the domain of 1 over x?
Negative infinity to 0.
Good, so it only discounts 0, right? That's the only thing you can't use is 0. What's the domain of the ln of x?
All positive, all real numbers.
All positive, I like all positive. Greater than 0, so it's not on this side too, right? Let me stop there for a second. You guys see what I'm talking about? And this is why several problems in your homework say, what's the domain of the first function and what's the domain of your derivative? Because the domain can certainly change. You guys kind of with me? But if I started here, my domain doesn't suddenly become bigger than it used to. It kind of inherits the problems that this guy had. All right, just want to make sure you guys are. So when we learn the reverse of differentiation, when I do whatever to this, when I anti-differentiate this, let me call that, I'll just call it anti-prime for right now. When I undo the prime, the answer is not going to be ln x. Because what's my original function's domain? Everything except 0. Holy shit, what happened here? So really, to be careful, I want to say, there. So that the domains still match. So that's going to come up later. I just want you to realize ln has got problems with its domain that the function that it came from doesn't. But now, if I start with ln, the domain is 0 to infinity. That's all it can be. If I look at this guy's derivative, what's happening? What's going on down here? What kind of slope is this? Way down here, what kind of slope is that? Tell me something about the slope. Positive. Big positive? Yeah, damn straight. And then does it ever come to 0?
No.
It can't. It actually can't. It's always going up. It's always increasing. So it's really big positive, and then it's getting less and less, and it's approaching 0. So it looks like that, which is exactly what 1 over x looks like on that side, right? It's not a proof. This is the proof. Well, that's kind of a visual confirmation. I like it. I like it. I like it. So what does this mean? Well, this means you can now get problems like this, for example. Find this guy's derivative for me. Actually ask you what this guy's domain is. Now, I'm curious about this because I'm about to do a problem where you can use properties of logs. This one you cannot. Hopefully you understand. Because what's being squared, the function that's inside the sine. If the sine was being squared, I could actually take that square down. Because then the natural log, it would be natural log of something squared, and that's when the 2 can come out. You guys with me there? Are you at all? Do you understand the difference there? So if I gave you this problem instead, I could take the 2 down, because now the argument of the log is being raised to a power. That's when the property of logs, this is the log of something to the first power, so the property can't hold. I don't care that the inside of this guy is, the inside of that guy could do any damn thing it wants to. The natural log is not going to be able to see it. It's inside the freaking sine. Here the ln sees a squared function, so that 2, first thing I would do before taking any freaking derivatives is get that sucker out of the way. It's awesome when things are not squared with derivatives, right? Take the power out of the way, things become easy. That's one chain rule link I don't need, right? If I left it up there and did it, it would have to come out to the same thing. It would. So let's finish this one up. What happens here? The ln is 1 over this mess times the derivative of this mess prime. There you go. So I get, what's the derivative of sine? Cosine of this times the derivative of this, which is 2x. And if you wanted to, you can write this as 2x cotangent of kick-ass. Yeah. I like that reaction. So, kind of look for that. I'm not going to take points off, but it's always nice when you realize you can make something more concise. Right? All right, you guys see that's nothing new. We just learned a new function's derivative, and the minute we learn a new function's derivative, holy shit, we're going to throw all this stuff at you again. Here's chain rules and product rules and stuff. And you're like, it's the same stupid rule. That doesn't change. I just have to use the 1 over rule that I just learned for that ln. Ooh, no big deal. So if you still suck with product and quotient and chain rule, there's just more of it's going to come at you now as we learn more functions, derivatives. So if I want to finish this guy out, what's g prime here? It's not too bad. It's good. Yeah, so it'll be 1 over sine, I like it, times, through the inside is just cosine, which is
2 cosine.
Kick-ass. I like it. Very different from this. Right? This was worse than that because that could be simplified first. Right? That was actually somehow less complicated. It didn't have a function inside of a function inside of a function. It didn't. It just had a function inside of a function. It was easier. Maybe. What's happening up there? Freaking me out. If you were looking at the ceiling over my head, I'm like, something's going to happen to me. So here, I don't know if you remember this, but I promised you a while back. Here's another example of ln's of logs. And in fact, we still have to talk about what the hell, what's the derivative of like log base 7. We don't know yet. But let's stick with ln's for a second. If I have this, what you got, Jeff? I don't know. Let's make there be, let's go this one. Oh, and even here, right? There. Yeah. Awesome. That's yummy. That's so yummy. What's the big deal? What's that? What's the big deal?
The 7 just come out.
It's just a 7. Right? It's not a power when it's an ln. I can just take it down and make it a freaking 7. It's not a 7th power anymore. Now, if you tried to attack this directly and didn't first simplify, that would so desperately suck. You would have to have 7 times this to the 6. It would be 1 over this times the 7 comes down times this to the 6 times the derivative of the inside, which is a quotient rule. We're going to be much better than that, right? We can not only can we bring the 7 down, what else can we do?
Don't they flip?
No.
When you start taking a derivative, do they flip or not?
No. You're thinking about, if I did leave it this way, listen, if I did leave it this way, it'd be 1 over this,
Okay.
which would be the reciprocal, but I don't have to leave it like this. What can it do with logs? What's the log of a quotient? Yes, ln of x minus 4 minus ln of x plus 3. I'm going to stop there for a second. What's the big deal? Now, of course, if your log properties are weak, another strengthen those bad boys up. So then what's this guy's derivative? Put a 7 on the outside. This is really nice. What's the derivative of this?
1 over.
And it's a linear function with a slope of 1. So its chain rule piece is going to be 1. It's awesome. Minus
1 over 2.
You can distribute the 7. You can find LCD if you wanted to. Whatever you have to do next. But for the derivative, you can stop there. I don't have anything to do next. Yeah. Now let me ask you this. Let me see if anybody can come up with this. Some of you already maybe know this rule, and this is definitely a very obscure rule. Does not mean it's not important. And you know that probably means I'm going to put this on the test. Can somebody come up with the rule for that? Log base A. Might mimic what we did for an ln, because that's just a specific case of a base. So let me write this as y. Yeah, right? These two you're done with?
Is it log A divided by log x?
Oh, you could do, yeah, sure, I like it. You could do the change of base formula, right? But if you did the change of base formula, you could be smart about it and use...
Quotient?
Well,
would it be like a to the y equals x?
so you could do this. You could use change of base. Cob. This would be... And you can use any log you want to. So which log would we probably use? ln. ln x over ln a. What goes in the bottom is the base, right? I love change of base formula. It's one of the easiest formulas to know. Put the base on the bottom.
But would it, can the ln's just cancel out or no?
What do you mean? So let's do this real quick. You guys with me on this? You guys remember this? So I like that suggestion. I wasn't even going to do that. But let's do this both ways then. If I continue this way, what is ln of a? What is it physically? Constant. Kick ass. So it just comes for the ride. So that's not a quotient rule. That's 1 over ln a times ln x. It's like 2 times ln x. Right? It's just a number times ln x. What's the derivative of ln x? And why does it make sense? Because the ln, its base is, ln's base is e, and ln of e is 1. And that's why derivative of ln is 1 over x, because that's just it.
Yeah.
But if I keep going this way, I could rewrite this as x equals
A
to the y. Then do this implicitly.
So 1y,
Derivative of a to the y is a to the y times ln a times dy dx. So let me stop there for a second. This whole thing is the derivative of a to something. This is the chain rule piece, right? I want you to realize which piece. So the first thing is you got to do the entire definition. Remember we did secant, and it was secant mess, tangent mess. Well, until you finish writing that whole thing out, you haven't started doing the chain rule piece yet. People always get those tripped out. But the derivative of secant is defined to be something weird. It's defined to be a product of two functions, one of which is itself again. That's kind of weird. But, oh, well, you just write the whole rule out, and then you attach the chain rule. Yes?
So it becomes dy dx equals 1 over hy ln of a? And is that it? Is that evaluated?
You tell me, is it the same as this?
Yeah.
It is eventually, because a to the y is x. Alright, let's see this in action in one example, and then we'll attack the inverse trig functions. Oh, yes. Oh, let's go this way. What you got, John? I don't know, John. Let's not make it too freaky. Yes, ma'am, sorry.
I just have a question because when you're asking, like, find dy dx, does that always mean implicit differentiation?
No,
'Cause that can be-
only if you can't get y by itself.
Okay.
So if I give you a function you could solve for y, and I'm not saying use anything, I just say find dy dx and you can solve it for y, hell yeah.
Okay.
Now if I say implicitly differentiate this, even if you could solve for y, I'm saying don't, just attack it. Yeah. So this thing I can't, well, this is not even part of it. This won't be implicit anyway, there's no y's in there explicitly. You guys start to realize the most important thing we're learning are the rules. Now you also have to know what every function itself does, but the rules